So thanks for this opportunity. The topic for today's conversation is around the power behind machine learning based forecasting, right? Or what's really so different, and how can it really help us in the demand forecasting space? So what's this power? We have heard a lot about it last year's forum. In the last year's forum, we also spoke a little more on this topic. So let's go into a little more specifics and the nuances of what has evolved in this space. So the need for machine learning is well established. Businesses are looking for these two aspects in terms of how can I improve what can be predicted, and the ones that the situations or events that cannot be predicted, how do I manage those? How do I get a good handle on those events, right? And businesses are looking for approaches where they can improve their forecasting, not just use the traditional statistical regression models, but how do I now leverage all the new data that's now available, both internally and externally? And can I start automating some of these processes? What more can I do with all the data that I have? Right? So there is a need definitely to go beyond what we have traditionally done in the forecasting space. Use the technology, use algorithms to help us out, and also learn over a period of time, like how a planner, how a user would learn. Can my system, can this algorithm itself learn over a period of time? We all understand, being practitioners in this space, experts, solution providers, consultants, we do understand the importance of improving the forecast accuracy. That kind of results in lower inventory, better fulfillment levels, and many other improvements, right? I mean, forecast improvement is just the starting of getting business benefits on various aspects. So understanding the need for improving demand forecasting, going beyond the traditional algorithms, is the first step, I would say, because that is what would now propel you to say, okay, what more can I do? Can I do something more than what I have been in the past? So in my view, I've kind of summarized this, that a good machine learning based forecasting approach, right? It consists of 5 elements. We'll go through each of these 5 one by one. The first one is the ability. The algorithm should have the ability to consider the interaction of different parameters, different influencing factors. Right? For example, if I build a traditional approach, a traditional algorithm, it would look at each of these influencing factors kind of in isolation. That, okay, how does promotion impact my sales, or how does the day of the month or day of a week, or how does the weather forecast or competitor activity, right? How are these parameters influencing my forecast? So this becomes kind of, although the final equations would have a mix of all of it, but the way the analysis gets done is where I try to start decomposing the impact of each of these factors on my final forecast. But a really good machine learning algorithm should be able to also understand the interplay of these events, right? For example, a sporting event happening on a weekend is different from a sporting event happening on a weekday, right? Or a competitor activity happening when I'm also running a promotion is different from when I'm doing a promotion on my own. Right? So there are different combinations, and they may actually have different impacts. So how do I make my algorithm understand these interactions? And that I would call as Blue Yonder secret ingredient, I mean, in our machine learning algorithm. So that's, I would say, the first element, what needs to be in that kind of an approach. The second very important element is what truly differentiates machine learning ML based approach to a traditional approach is also to be able to understand the interaction between the different hierarchies of products, locations, channels, and all of it, right? So what it means is that traditional forecasting approaches would look at, say, a given item at store combination, or I would look at, say, a product category or a product class and a region intersection, look at the time series for that intersection, and come up with an equation that would help me forecast. But what ML can actually help us do is also also understand how do these interact with each other, right? In our traditional sense, we talk about the halo effect or cannibalization effects and all those kind of things, right? So can the algorithm learn that if a particular item at a given store is doing well, then in all likelihood there are 10 other items which are also going to be doing well because they have a kind of a rub-off or a halo effect happening on those intersections also, right? So it's not so easy to model these kind of interactions in a traditional approach. But with machine learning, this becomes easier, where it can understand, say, overall at that particular store or in that particular DC or in a region, does price play a larger role or not? Now, I don't need to tell the algorithm on what are the intersections to check for. A good algorithm would automatically detect these kind of aggregation points, the summarization points, and figure out on its own on are there interactions or impact which are going across the different hierarchies or across different intersections, right? So that I would say is the second key element, what is essential or what should be in a good ML based forecast. Not just that, there is also the whole new product planning or new product introduction. A good ML algorithm should also be able to detect that is this a continuation of a similar product of the past, right? So without me trying to give too many inputs, a good ML would actually figure out that yes, this is a new product which has been introduced, and if I look at the attributes of this product and some of the other products where I saw the sales going down, it starts inferring that this is a likely continuation of a previous product. And we actually tested this out with one of the electronics companies earlier in the year, and they gave us data which was masked, so we did not really know what was the underlying product. So they were dummy product names, but the history was real, and the algorithm is actually able to understand and infer, and we were quite very accurately able to connect that this was the old product and this is the new product into which it has transitioned. And that was quite surprising for the customer to for the business to actually see that an algorithm can actually detect such kind of relationships. So that's the second one. What's the third element here is, again, a traditional approach would start looking at forecasts at, say, a higher time dimension, say a weekly forecast or a monthly forecast, and then breaking it down to a day level. But a good forecast, a good ML forecast should have the capability to actually consider the data and create a forecast at the day level natively. I mean, natively in the sense, it's not a breakdown which I'm doing from a higher level, but really considering the day level sales and forecasting at the day level, right? So that's a true a native day level forecast is what I would call, and that should be an inherent capability in an ML based approach, right? The major drawback or the major challenge which most of the businesses or data scientists also face is to be able to explain the ML forecast. Right? So if a user, if a planner actually comes back and asks that, okay, help me understand why did I come up with this number, right? What was the basis? Because that's how we are trained to think that. What are the influencing factors? How much did it influence? So if the price changed a little more, would it actually impact my demand more than what I'm seeing, right? So the explainability of machine learning algorithms is the fourth critical aspect that should be in there. And as you see here on a screenshot, right? So for example, I see a future forecast. Okay, is it primarily getting influenced by the event or the price or weather, or what really is influencing my future forecast? And the fifth is what we have also been discussing in the past or even earlier in the day today around the whole probabilistic forecasting, right? So as you see these two distributions of forecast, it has the same average value, the same mean value. But as you can very clearly make sense of, the way I would treat the first product on the top, which is with the lower uncertainty, which has a very tight distribution, as compared to the other product, which is on the bottom part of the screen, which has a very high degree of uncertainty and a large tail on the probability. I would treat them differently, right? So even though they have the same average value, which a traditional approach would give me, but my treatment in the supply planning would be very different. So hence, getting a view of what's the underlying the probability distribution function of that forecast element, right? And now what I'm really talking about is if you try to combine point number 3 and 5, you really need a very, very strong ML algorithm here, right? To be able to do this at every intersection at the day level is not an easy task, right? I mean, it needs to be, the algorithm itself needs to be very scalable and very robust, right? So I would say these are the 5 elements that should be in a good ML algorithm used for demand planning or for demand forecasting. Faced with the current times of COVID and all the disruptions that we are going through, does it work? So we actually have a few customer quotes. I cannot put the names here for proprietary, for confidentiality reasons. But there were some of our customers that we were working with who had implemented these algorithms before COVID, right? So what they actually reported back are this kind of a feedback, right? That the algorithm is able to adapt to this new situation or the new sales pattern that it's observing. So they did not really find the need to put any kind of overrides in there. When they saw that some stores were performing differently from other stores, the model is also, it was able to catch this nuance. On the inventory side, what some of our customers who were using this found that they were actually experiencing better fill rates, better service level performance on categories where they had already started using the ML-based algorithms. And they actually found it to be easy in terms of working, that they could just allow the system to run, and the planners were then just focusing on making sure the supplies are aligned to what my forecasting models are saying. Right? And the third aspect around automation, this particular customer was wanting to put some overrides, but then they figured out that the model had already caught the trend, and they were already reacting to the changed scenario. So they did not have to actually put overrides into the system. Right? So these are some. So the question basically kind of answers the question that does this work in a turbulent situation or in such kind of a large scale disruption? It does. I mean, that's what we have seen. And what I would even go to the extent of saying that these kind of disruption events, like what Peter also said, that I mean, it's not the time to throw all this and really go back to a war room kind of a situation. But these are probably events which should compel us to focus on improving the algorithm's capabilities, improving the processes underneath that would help us utilize these numbers and get the business benefits that we are looking for. Just to summarize again, the value, definitely it was what we talked on the first slide. Businesses have actually seen that kind of improvement in accuracies, and not just the forecast accuracy, right? Because forecast is, like all of us know, it is just the starting point in my entire planning cycle, right? So actually deriving value in terms of the final growth, in terms of inventory reduction, wastage reduction, and all of and the margin improvements, that is what one would actually see at the end of the day. And this is something which at least the businesses that we are working with who have taken on machine learning as their default approach have started seeing. So just last point here, I mean the last slide from my side in terms of how, okay, now that we understand there is a benefit in using machine learning, so how do we make this work? Are there certain guidance, certain guidelines that we need to be aware of, right? So it needs to be accurate by definition. I mean, if we are going to move from a traditional approach to a good ML algorithm-based approach, it should give us better accuracy, definitely. With minimal effort, to the level possible, I should be able to automate. It should be able to deliver results. There has to be a robustness. So we all also know the common phrase in terms of garbage in, garbage out. But now the question has moved beyond that. The question now is that my data is going to have outliers. It's going to have input which may not be reasonable, which may go beyond the normal conditions that are expected. So is my algorithm itself able to now figure out these kind of outliers and treat them appropriately? Right. So I cannot now go back in today's age to say, oh, there were too many outliers in the data and hence I could not make it work. Right. So the algorithm itself needs to be intelligent enough to find a way to deal with these outliers. Right. And ML, it should also make sure that we are not overfitting, right? Because overfitting would then lead to it would not be able to catch trends as they keep changing, because it's really looking at, or kind of memorizing is the right word, that it's completely memorizing a past pattern rather than trying to extract or abstract out a pattern from there. And the other pieces we talked about, that it has to be explainable and has to be something that can be run with minimal intervention from planners or from people in the organization, right? And just the last point here is that the kind of intersections and the granularity that we are talking about, it has to be scalable, right? Today, what we commonly kind of joke about or talk about is the biggest competition is the do-it-yourself kind of an approach that many organizations may have. Because of the ease of creating programs for data, using data science algorithms. There's so many libraries, so many packages which are available free on the internet. It gives us, I would say, a little bit a false sense that I can do it on my own. I don't need any expert to come and tell me what should be done. So while I agree that this may be useful when it comes to prototyping or creating POCs, but when you actually have to run it in a production environment, it has to be robust, it has to be scalable, it has to be production grade, right? It has to be tested for all those capabilities, all those skills, fail proof. Right, it requires a different level of robustness inside, as opposed to something which a person would just write in their spare time, or maybe in a 1 month, 2 month kind of prototyping. So that's what I would end with. We at Blue Yonder do believe the AI or the ML in the supply chain can really help save the world. And that's what our theme is when it comes to using all these algorithms to improve sustainability in the supply chain across the world and making this a better place. That's all I had. Thank you. If there are any questions, we could take